गुड मॉर्निंग स्टूडेंट्स। आज हम लोग पढ़ेंगे चैप्टर नंबर 12 एटम। तो सबसे पहले एटम के बारे में जानते हैं। एटम होता क्या है? द स्ट्रक्चर ऑफ मैटर दैट शेप्स द वर्ल्ड अराउंड अस हैज़ बीन a subject of study since long time. The first contribution in this regard came from Dalton, who postulated the matter is made of atoms, which are indivisible. The word atom comes from a Greek word atoms, which means no cut. J.J. Thomson proposed a structure for the atom which was modified by Rutherford and later by Niels Bohr. Dalton's atomic theory. All elements are consist of very small invisible particles called atoms. Atoms of same element are exactly same and atoms of different elements are different. Thomson's atomic model. Every atom is uniformly positive charged sphere of radius of the order of 10 raised to power minus 10 meter, in which entire mass is uniformly distributed and negative charged electrons are embedded randomly. The atom as a whole is neutral. This was also known as plum pudding model of an atom. Limitations of Thomson's atomic model. It could not explain the origin of spectral series of hydrogen and other atoms. It could not explain large angle scattering of alpha particles. Rutherford's alpha ray scattering experiment. An alpha particle is helium nucleus containing 2 protons and 2 neutrons. Therefore, an alpha particle has 4 units of mass. This experiment was done by Rutherford and his collaborators Geiger and Marston and is shown in below figure. Here is the figure of experiment which was performed by Geiger and Marston. Conclusion. A typical graph of the total number of alpha particles scattered at different angles in a given interval of time is shown in figure. The dots in this figure represent the data points. Here are a graph between scattering angle and number of scattered particles. Many of alpha particles pass through the foil. It means that they do not suffer any collisions. Only about 0.14% of the incident alpha particles scatter by more than 1 degree and about 1 in 8,000 deflect by more than 90 degree. Rutherford argued that to deflect the alpha particle backwards, it must experience a large repulsive force. This force could be provided if the greater part of the mass of the atom and its positive charge were concentrated tightly at its center. This led Rutherford to postulate that entire positive charge of the atom must be concentrated in a tiny central core of the atom. This tiny central core of each atom was called atomic nucleus. Here are the observation and conclusion of Geiger-Marston's experiment. Observation number first. Most of the alpha particles passed straight through the gold foil. Conclusion. It indicates that most of the space in atom is empty. Observation number 2. Some of the alpha particles were scattered by only small angles of the order of a few degrees. Conclusion. Alpha particles being positively charged and heavy compared to electron could only be deflected by heavy and positive region in an atom. It indicates that the positive charge and the most of the mass of atom are concentrated at the center called nucleus. Observation number 3. A few alpha particles, 1 in 9,000, were deflected through large angles even greater than 90 degree. Some of them even retraced their path, that is, angle of deflection was 180 degree. Conclusion: alpha particles which travel towards the nucleus directly get retarded due to Coulomb's force of repulsion and ultimately comes to rest and then fly off in the opposite direction. Distance of closest approach. Distance of closest approach is the minimum distance between alpha particle and center of nucleus just before it reflects back by 180 degree. When the distance between alpha particle and the nucleus is equal to the distance of the closest approach r0, the alpha particle comes to rest. At this point or distance, the kinetic energy of alpha particle is completely converted into electric potential energy of the system. That is, the kinetic energy is equal to Coulomb's electrostatic energy. That is, 1 upon 2 mv square is equal to 1 upon 4 pi epsilon naught ze square upon r naught, or r naught is equal to 1 upon 4 pi epsilon naught 2 ze square upon mv square. Obviously, the radius of nucleus must be smaller than above value. Impact parameter. The trajectory traced by an alpha particle depends on the impact parameter b of collision. The impact parameter is the perpendicular distance of the initial velocity vector of the alpha particle from the central line of the nucleus. For large impact parameters, force experienced by an alpha particle is weak as f varies inversely as square of distance and alpha particle will deviate much smaller and vice versa. Rutherford calculated the impact parameter b is equal to 1 upon 4 pi epsilon naught ze square cot theta by 2 upon ek. Rutherford's model of an atom, which is based on its alpha scattering experiment. An atom is composed of positively charged particles. Majority of the mass of an atom was concentrated in a very small region. This region of the atom was called as the nucleus of an atom. It was found out later that the very small and dense nucleus of an atom is composed of neutrons and protons. Atom's nucleus is surrounded by negatively charged particles called electrons. The electrons revolve around the nucleus in a fixed circular path at very high speed. These fixed circular paths were termed as orbits. An atom has no net charge, or they are electrically neutral because electrons are negatively charged and the densely concentrated nucleus is positively charged. A strong electrostatic force of attraction holds together the nucleus and electrons. The size of the nucleus of an atom is very small in comparison to the total size of an atom. Electron orbits. The electrostatic force of attraction Fe between the revolving electrons and the nucleus provides the requisite centripetal force Fc to keep them in their orbits. Thus, for a dynamically stable orbit in a hydrogen atom, Fe is equal to Fc, that is mv square upon r equal to ze square upon 4 pi epsilon naught r square, or we got T is equal to mv square upon 2 equal to ze square upon 8 pi epsilon naught, where T is kinetic energy Potential energy U is equal to minus ZE square upon 4 pi epsilon naught R. Thus, total energy T plus U equal to minus ZE square upon 8 pi epsilon naught R. For hydrogen atom, we know Z equal to 1. So, E is equal to minus E square upon 8 pi epsilon naught R. The total energy of the electron is negative. This implies that the electron is bound to the nucleus. Atomic spectra. When an atomic gas or vapor is excited at low pressure, usually by passing an electric current through it, the emitted radiation has a spectrum which contains certain specific wavelengths only. A spectrum of this kind is termed as line emission spectrum, and it consists of bright lines on a dark background. When white light passes through a gas and we analyze the transmitted light using a spectrometer, we find some dark lines in the spectrum. These dark lines correspond precisely to those wavelengths which were found in the emission line spectrum of the gas. This is called the absorption spectrum of the material of the gas. Spectral series of hydrogen. Hydrogen is the simplest atom and therefore has the simplest spectrum. In the observed spectrum, however, at first sight, there does not seem to be any resemblance of order of regularity in spectral lines. Each of these sets is called a spectral series. In 1885, the first such series was observed by Swedish John Jacob Balmer in the visible region of the hydrogen spectrum. This series is called Balmer series. The line with the longest wavelength, 656.3 nm, is the red is called H alpha. The next line with wavelength 486.1 nm in the blue green is called H beta. The third line 434.1 nm in the violet is called H gamma, and so on. Balmer found a simple empirical formula for the observed wavelength 1 upon lambda is equal to R 1 upon 2 square minus 1 upon n square, where n is equal to 3, 4, 5 and so on. R is a constant called Rydberg constant, or R is equal to 1.097 into 10 raised to power 7 meter inverse. Other series of spectra for hydrogen were subsequently discovered. These are known after their discoverers as Lyman, Paschen, Beckett and Fun series. These are represented by the formulas for Lyman series 1 upon lambda equal to R 1 upon 1 square minus 1 upon n square, where n is equal to 2, 3, 4 and so on. This series is in ultraviolet region. Paschen series 1 upon lambda is equal to R 1 upon 3 square minus 1 upon n square, where n is equal to 4, 5, 6. This is in infrared region. Bracket series 1 upon lambda equal to R 1 upon 4 square minus 1 upon n square, where n is equal to 5, 6, 7. This is also in infrared region. Fun series 1 upon lambda equal to R 1 upon 5 square minus 1 upon n square, where n is equal to 6, 7, 8 and so on. It is also in infrared region. Limitations of Rutherford atomic model. It cannot explain stability of atom. According to classical electromagnetic theory, an accelerating charged particle emits radiation in the form of electromagnetic waves. The energy of an accelerating electron should therefore continuously decrease. The electron would spiral inward and eventually fall into the nucleus. Thus, such an atom cannot be stable. It cannot explain line spectra of atom. Further, according to the classical electromagnetic theory, the frequency of the electromagnetic waves emitted by the revolving electron is equal to the frequency of revolution. As the electrons spiral inwards, their angular velocities and hence their frequencies would change continuously, and so will the frequency of the light emitted. Thus, they would emit a continuous spectrum in contradiction to the line spectrum actually observed. Bohr's model of an atom. Niels Bohr made certain modifications in this model by adding the ideas of the newly developing quantum hypothesis. Postulates of Bohr's model. Every atom consists of central core called nucleus in which entire positive charge and almost entire mass of atom are concentrated. A suitable number of electrons revolve around the nucleus in circular orbits. The centripetal force for revolution is provided by electrostatic force of attraction between electron and the nucleus. Electron revolves around the nucleus only in those orbits for which the angular momentum is same integral multiple of h upon 2 pi where h is the Planck constant. Thus the angular momentum L of the orbiting electron is quantized, that is L equal to nh upon 2 pi. An electron might make a transition from one of its specified non-radiating orbits to another of lower energy. When it does so, a photon is emitted having energy equal to the energy difference between the initial and final states. The frequency of the emitted photon is then given by h nu equal to Ei minus Ef. Radii of Bohr's stationary orbits is given r equal to n square h square upon 4 pi square m k z square. This shows that r is directly proportional to n square upon z. If the radii of stationary orbit are in the ratio 1 square, 2 square, 3 square, and so on, clearly the stationary orbits are not equally spaced. Putting values of all constants, we get Rn equal to 5.29 into 10 raised to power minus 11 meter n square upon z. This is called the Bohr's radius. Velocity of electron in Bohr's stationary orbit is given v equal to 2 pi k z square upon nh. This shows r is directly proportional 1 upon n. Therefore, orbital velocity of electron in outer orbits is smaller as compared to its value in the inner orbits. For hydrogen, z equal to 1. Therefore, v equal to 2.2 into 10 raised to power 6 meter per second. Frequency of electron in Bohr's stationary orbit. It is the number of revolutions completed per second by electrons in a stationary orbit around nucleus and is given by nu equal to kz square upon nhr. That is, nu is directly proportional 1 upon n. The first orbit of hydrogen atom, nu equal to 6.57 into 10 raised to power 15 rps. Total energy of electron in Bohr's stationary orbit is given E equal to minus 2 pi square m k square E4 upon h square z square upon n square. Putting standard values, we get E equal to minus 13.6 z square upon n square eV. For hydrogen, E equal to minus 13.6 upon n square electron volt. For ground state, E equal to minus 13.6 electron volt. Therefore, the minimum energy required to remove the electron from ground state of hydrogen atom is 13.6 electron volt. This is called ionization energy of hydrogen atom. Bohr's expression of spectral series. According to third postulate of Bohr's theory, when an electron makes a transition from orbit of higher energy to lower energy orbit, a light photon is emitted. When an electron jumps to its first orbit from any other orbit, that is Lyman series is obtained, which lies in ultraviolet region. nu equal to r 1 upon 1 square minus 1 upon k square, where k is equal to 2, 3, 4. Similarly, when an electron jumps to second orbit from any other orbit, Balmer series is obtained, which lies in visible region, nu equal to r 1 upon 2 square minus 1 upon k square, where k is equal to 3, 4, 5. When an electron jumps to third orbit from any other orbit, Paschen series is obtained, which lies in infrared region. When an electron jumps to fourth orbit and fifth orbit from any other orbit, and bracket and Pfund series are obtained, respectively, which also lies in infrared region. Energy level diagram. A diagram which represents the total energies of electron in different stationary orbits of an atom is called energy level diagram. An electron can have any total energy above E equal to 0 electron volt. In such a case, the electrons is free. Excitation energy. The minimum energy required to excite an atom in the ground state to one of the higher stationary state is called excitation energy. Example, in case of hydrogen, to lift an electron from ground state to first excited state, energy is E equal to minus 3.4 minus 13.6 equal to 10.2 electron volt. Excitation potential. The minimum potential which provides an electron energy sufficient to jump from ground state to one of the higher state is called excitation potential. Excitation potential is equal to 10.2 volt. Ionization energy. The minimum energy required to ionize an electron is called ionization energy. Ionization potential. The minimum potential which would provide an electron to just remove an electron from one atom is called ionization potential. Limitation of Bohr's model. The Bohr model is applicable to hydrogen atoms. It cannot be extended even a two electrons atom such as helium. Difficulty lies in the fact that each electron interacts not only with the positively charged nucleus but also with each other. While the Bohr's model correctly predicts the frequencies of the light emitted by a hydrogen atom, the model is unable to explain the relative intensities of the frequencies in the spectrum. Thank you. Have a nice day.